ahead.
Okay, so now it's all right.
Yeah, good.
Okay,
yeah, thank you.
So this is Rong Yu from Renmin University of China, and first thanks organizers for inviting me to give this talk here to this symposium. And today I would like to talk on the orbital selectivity, and we actually started from the iron trichronized system to the iron nuclide system recently. Okay, so these are my collaborators. Mr. Lin Hui Hang is a graduate student in my group. And for the theory part, we also collaborated with Dr. Jianxin Zhu at Los Alamos National Lab and Professor Qimiao Xi's group at Rice University. And we also collaborated with the Professor Ming Yi's group at Rice University on the RPAS experiment. So here's a outline. I will give a very brief introduction to the electron correlation effects in the iron-based superconductors, with focusing on the orbital selectivity, which is actually a multi-orbital correlation effects for the multi-orbital systems. And I will mainly talk on the orbital selectivity in both the iron triquartinite system, in this doped iron selenide system, and also on this iron nictide system. It's a lithium-111. And in particular, we find that the orbital selectivity will give the very strong renormalization of the electronic structure and the reduction of the Fermi surface in this compound. And at the end of this talk, a summary will be given. Okay, so shortly after the discovery of the high temperature superconductivity in the iron nictides, it has been recognized that this system consists of considerable strong electron correlations, as one can show here in this optical conductivity data. The Druid weight is considerably suppressed from the band theory values. So this will suggest, this actually suggests that the parent iron nictide system is actually a bad metal. And another evidence of very strong electron correlations in these iron-based superconductors, it can be actually seen from this global phase diagram of this system. So the superconductivity actually appear close to a antiferromagnetic ground state, which actually suggests the antiferromagnetic spin exchange interactions is very important for the superconductivity in these systems. Okay, but besides the antiferromagnetic spin exchange couplings, we have to also recognize that the iron-based superconductors are multi-orbital systems because the Fermi surface consists of multiple sheets with both hole pockets at the center of the brane zone and also these electron pockets at the boundary of the brane zone. And also the multiple orbitals, the 3D orbitals of irons are not all degenerate. It's actually a partially degenerate with doubly degenerate XZ and YZ orbitals, and all the other 3D orbitals are actually non-degenerate. So this is a very complicated multi-orbital model. So if we started from a theory, we'll see that we can consider actually a multi-orbital Haber model for the iron-based superconductors. It consists of the non-degenerate orbitals with a finite interorbital kinetic couplings. And also, if you look at the interaction part, it consists of competing interactions with the intraorbital Coulomb repulsion and also the interorbital Coulomb repulsion, and also very importantly with this Home-through coupling interaction. And this will give a very rich physics for this model. And for example, depending on the strength of this Holmes-through coupling and the strength of the level splitting, the delta, the system can be either stabilized in a high spin state or in a low spin state. So it is actually natural to expect that the correlation, the strength of the electron correlations are actually very strongly orbital dependent, means that they are not the same for all the 5 iron 3D orbitals. And then we actually need to identify which orbitals are the most important for the magnetic order or the antiferromagnetic order, and also for the superconductivity in these systems. So we actually first focus on the normal state properties. In general, if we consider a multi-orbital system, say let's consider 2 orbital system, if there is a very strong orbital dependent electron correlation effects in these systems, we call this system has a very strong orbital selectivity. And in the extreme case, one orbital can be in a metallic phase with a itinerant electrons in this orbital, but the other orbital can be inside a most insulating phase, where the only active degree of freedom are the spins, but not the charge degree of freedom. Okay, so we call this system is in a orbital selective mode phase. Okay, but in the experiment, usually the different there are hybridizations between the different orbitals, and then the orbital selectivity can be measured, or usually measured by this effective mass renormalization factor, the m star over mb. If we see a very strong orbital dependent mass renormalization factor, usually this corresponds to a strong orbital selectivity, which is a precursor to the orbital selective mode phase. So in the iron-based superconductors, this orbital selectivity has been extensively studied, both theoretically and experimentally. And especially for the experiment, it has been recognized that the orbital selective mode behavior is kind of universal behavior for all the iron trigonionized system, both for the doped iron selenide system, or the single layer iron selenide system, or this potassium iron selenide system. And in all these systems, when increasing the temperature, the system seems to goes from a bad metal phase to a orbital selective mode phase, as shown in this very nice paper by Professor Ming several years ago. And how to study this orbital selective mode physics theoretically. And here we propose to solve for the 5 orbital Hubbard model for the iron-based superconductors by using the so-called U1 slave spin formulation. So here is the model. It consists of a tight binding part and a interaction part with the U prime, and the J Holmes terms. And in the U1 slave spin theory, we introduce a quantum spin 1/2 operator to carry the charge degree of freedom, and also a fermionic spin-on operator to carry the spin degree of freedom, and to rewrite the electron creation operator in terms of this slave spin and this fermionic spin-on operators. And we also introduce a constraint to limit the Hilbert space in the physical sector. And to get the saddle point solution, we rewrite this electron creation operators in terms of the Z addressed slave spin operator and a fermionic spin-on operator. So here the address operator is proportional to this slave spin operator previously introduced. And then at the saddle point level, we obtain 2 Hamiltonians, one for the spin-on sector and the other is for the slave spin sector. And we solve these two Hamiltonians self-consistently. And we can get basically three different solutions. So if the quasi-particle spectral weight, the Z, are all non-zero for all the orbitals, the system is in a metallic phase. And if the quasi-particle spectral weight Z is zero for all the orbitals, this is a multi-insulator. And interestingly, we also find there is a third solution which corresponds to this orbital selective mode phase. So in this phase, for some orbitals, the quasi-particle spectral weight becomes a zero, but for other orbitals, it becomes a non-zero. Okay, so we first apply this U1 slave spin method to study the electron correlation effects in this potassium iron selenide system. And here is the ground state phase diagram. And we can identify the three phases: a metallic phase, a multi-insulator phase, and in between there is an orbital selective mode phase. So inside this orbital selective mode phase, we see that the quasi-particle spectral weight in the XY orbital becomes zero. Means that this orbital is inside a multi-insulating phase, but all the other 3D orbitals of irons are still itinerant with a finite quasi-particle spectral weight. And we also find that for this potassium iron selenide system, the orbital selective mode phase can be induced by increasing the temperature, and from a bad metal phase to this orbital selective mode phase. Okay, and this is also seen by the RPAS experiment. Okay, so more recently, we look for a orbital selective mode phase which can be stabilized as a ground state in the iron trigonalite system. So we collaborated with Professor Ming Yi's group on this compound, this iron selenide system doped with tellurium. So we can actually find a orbital selective mode transition from a bad metal phase to a orbital selective mode phase by doping from the iron selenide side to the iron telluride side. And at the same time, we find that across this orbital selective mode transition, there is a reconstruction of the Fermi surface. So for example, for x equals 0.5, we see there is this faint, but still we can see this dxy like whole, very big whole pocket centered at the gamma point. But once we are inside this orbital selective mode phase, when x equals to 0.1, we see that the Fermi surface consists of ellipse centered at x point. So for the details of the experiment, I'll refer to this talk by Dr. Huang in this same section. And also I refer to our recent paper post archive. Okay. And why there is this reconstruction of the Fermi surface in this iron trigonalite system? And we can take a further look about the band structure in this system. So for x equals 0.5 in the bad metal phase, we see the dxy orbital is strongly renormalized. And because the dz square and the dxy are hybridized along this gamma to x direction, which corresponds from the zone center to here. And then we'll see that once the dxy orbital becomes strongly renormalized, this will actually push the dz square to be closer to the Fermi level. And for x equals 0.1, when the system becomes inside this orbital selective mode phase, the dxy orbital becomes totally incoherent. And then this will lead the dz square band to cross the Fermi level, which give rise to the reconstruction of the Fermi surface. Okay, so this is what happens in the iron trigonalite system. So now I will transfer to the orbital selectivity in the iron pnictide system. So we are actually looking for a system with also exhibit a strong orbital selectivity. And also we asked whether we can find a signature of the electronic reconstruction caused by the strong orbital selectivity in any iron pnictide system. And we actually find a very interesting experimental result given by Miao et al. In this paper. And they actually find a very strong temperature-dependent spectral weight evolution. So when increasing the temperature, they see the spectral weight in the XY orbital becomes reduced. However, the spectral weights for the XZ and YZ orbital almost keep a constant in this lithium-111 compound. So we studied the orbital selectivity in this lithium-111 compound. And another point which motivates us to study this system is the reduction of the Fermi surface in the lithium-111. So according to the DFT calculation, there are 3 hole pockets centered at a gamma point. However, in the experiment, they actually find that the lower the band, which is the alpha prime band, which account for the innermost hole pocket, is actually below the Fermi level. And even in a study by Professor Rosa Volantis' group, even they perform this DFT plus DMFT calculation, it doesn't seem to change too much from this DFT results. However, if they apply this non-local electron correlation effect using this TPSC method, and then they see the reduction of all the electron and hole pockets, and also the inner pockets becomes reduced. So this raises a very interesting question that whether one really needs this non-local electron correlation effects to see this reduction of the Fermi surface. Okay. So here are our results on the orbital selectivity in the lithium-111 system. So here is the ground state phase diagram. And this is very similar to the phase diagram in the iron tricoordinate system. We actually identify a very broad regime where the ground state can stabilize an orbital selective mode phase, even for this lithium-111 compound. And the nature is also similar. So inside this orbital selective mode phase, we see the DXY orbital has a 0 quasi-particle spectral weight, which means that this is already most localized, while the other orbitals are still itinerant. You know, why we see such a strong orbital selectivity in this lithium-111? However, we did not see the similar behavior in, say, this 1111 compound. We actually compare the density of states projected to this DXY orbital and versus the total density of states in these 2 systems. And actually, we indeed find that the density of states projected to the DXY orbital in the lithium-111 is getting narrower, much narrower than the 1111 compound. And this is actually because in the lithium-111 compound, the iron arsenic bond angle is much smaller. And because of this smaller bond angle, this will reduce the interorbital hopping associated with the DXY orbital and give a narrower band width. And this will account for the calculated the strong orbital selectivity in this lithium-111 compound. Okay. So given the proximity to this orbital selective mode phase at the ground state, we expect to see a transition from a band metal phase to a to a orbital selective mode phase by increasing the temperature. And this is indeed shown as in the calculated result. And we can identify a orbital selective mode transition at about 230 Kelvin, where the dxy orbital becomes fully localized, while the dxz and yz orbitals are still almost itinerant. The quasi-particle spectral waves of the dxz and dyz orbital almost keep a constant. So as observed in the RPS experiment. And now we turn to the renormalization of the band structure. So we find that the strong orbital selectivity not only lead to the strong renormalization of the bandwidth, but also lead to the renormalization of the energy levels, as shown in this plot. So for both the dxz orbital and the dxy orbital, we see a strong renormalization of the energy levels. And I'll show here that this strong renormalization of the energy level will cause the reconstruction of the Fermi surface. So close to the gamma point, the dispersion of the whole bands can be approximately written in this way. So it includes a non-interacting Fourier component of the hopping parameters, which is renormalized by the quasi-particle spectral weight at orbital alpha, and then plus a level energy. So it's which is also renormalized in this way. However, if there is a strong orbital selectivity, the renormalization factor Z prime is going to be different from the Z, from the quasi-particle spectral weight. It's a complex function of the quasi-particle spectral weights of all the orbitals, actually. So means these two are different, okay? And then this will lead to the reconstruction of the Fermi surface in the presence of finite electron correlations. So we first determine the Kf at u equal to 0. So then this is determined by this equation. So the C alpha plus this epsilon alpha equal to 0. And in the presence of electron correlation with finite u, the Kf is actually determined by requiring the dispersion E of K equal to 0. So that means that the entire thing becomes a 0. And we see that if there is a strong orbital selectivity, that Z prime is not equal to Z, and then this will lead to the Kf not equal to the Kf 0. So this will immediately give us the reconstruction of the Fermi surface. And then this is indeed shown in our calculation. And especially we find two features. One is all the pockets, including both the whole pockets and the electron pocket, just shrinks. And then most interestingly is for the inner pocket, the innermost whole pockets, we find that it's fully eliminated if we apply a finite u, where there is a pretty strong orbital selectivity. Okay. And to see this, a reconstruction of the Fermi surface is indeed associated with strong orbital selectivity. We take a closer look at the band structure at u equal to 0 limit and at finite u. And we focus on the band, the bottom of the gamma band, which has mainly a XY orbital character. And we find that it is renormalized by a factor of about 5. However, for the delta band bottom, which mainly has the dxz and yz orbital character, it only renormalized by a factor about 2. So this indeed shows a very strong orbital selectivity in this system. Okay, and we also find that there's also this strong renormalization of the dxy, this beta band close to the gamma point, and also this will push the dz square band to be closer to the Fermi level. And this is very similar to the case of the iron trigononite system. Okay, so then here is a summary of my talk. We studied orbital selectivity in multi-orbital models for both the iron trigononite and iron pnictide system. And we indeed find some universal properties in these two systems. And in particular, for the lithium-111 compound, we find the reduction of the Fermi pockets, which is associated by the strong orbital selectivity. And this can be understood by including the local correlations alone. And I would also say some words on the superconductivity. Basically, the main driving force for the superconductivity is the spin exchange, antiferromagnetic spin exchange couplings. However, in the case of strong orbital selectivity, the superconductivity both is a pairing structure and the gap structure can be strongly influenced by the orbital selectivity, which lead to this orbital selective superconducting pairing. Okay, and thank you very much for your attention.
Yeah, any questions for Rong?
Yeah, I have a question.
Okay.
So can you actually, both for Ming-Yi and for Rong Yu, what is the position of the XY level relative to the XZYZ in the chalcogenides in your calculations? Because my understanding is that many experimentalists claim that the XY orbital is below the Fermi level, not above.
Right. That's right. So you can see actually from here. Yes. So actually for this model for the FET-SE, actually this is the blue portion is actually the DXY.
Yeah. So
and then it actually cross because there is a finite orbital spin orbital coupling. So it's not this one, but actually goes this way. In the model, it is still slightly above the Fermi level, but I think this is I don't know. This is probably just a detail of this model. But it's pretty close. Yeah.
But I just want to know who to believe, because I agree this is a detail, but now I mean at this level of calculation is just a question of detail. So are they experimentally sure that the DXY, that this is not correct and the DXY lies below? So the DXY pocket is smaller than the XZYZ pocket.
Sure. I think for this experimental part, since I did not prepare a experimental slide, so maybe you can see the result in the next talk. I think it's pretty close to the Fermi level. That's a conclusion, which can result to this whole pocket.
So this doesn't agree with other experimental groups. I mean, I don't have a horse in the race. I mean, I haven't worked on that for 12 years. So I just want to know what is true.
I think the theorists probably should let experimentalists address this.
Yeah.
I guess so there is a hybridization which is seen between the XY whole band and the XYZ whole band near the gamma point, at least for the optimal substitution level, which I guess you can probably see from the cut in the next talk.
But for the iron telluride, do we know the answer?
I don't have the data in front of me, but I guess maybe after the next talk, when we see the slide, we can come back to this point.
Because again, if there's an orbital selectivity, there should be no hybridization. If you're really deep in the mod phase. Right.
So as we see tuning towards iron tellurium, we see the hybridization. We don't see the hybridization as much. I mean, there will come a slide. Sorry, my it's going to talk. We have the slides ready, but there will be a slide on the cut as a function of the substitution level.
Okay. So let me ask you, Rong. I mean, are you for the lithium iron arsenide? Are you also suggesting which orbital is responsible, DYZ or DXZ?
Responsible for what?
For superconductivity.
Oh, that's a good point. Okay, that's very good point. Very good question. So for this one, I think at least there is there is a reconstructed Fermi surface. Means that the innermost one is actually does not exist, right? So actually means that this I think will challenge this Fermi surface nesting picture. So I do think that the dxy orbital will contribute to this superconductivity.
Oh, to the pairing?
To the pairing, yeah. But we haven't did this calculation. We are going to do this. Yeah.
And here another question from an experimental perspective and a theoretical perspective. Once you are in the orbital selective mode phase, are you saying that the experimental Fermi surface violates the Latinger theorem?
No, at least theoretically it's not.
No, sorry. Once you are in the orbital selective mode phase, you should violate the Latinger theorem.
I don't think the Latinger theorem is violated.
Well, the XY is kicked out, so in that sense, I guess it is, right?
Yeah, it is. I mean,
it
you
is,
have to violate the Latinger theorem.
In practice, you have to fight the magnetic order, but
okay, but yeah, okay. It actually depends on how you count the number of the electrons. Yeah, sure. In that way, I think you're right. It is violated in that way. Yes. Yeah.
Okay.
Experimentally, Mingyi, did you really check the Latinger volume? In the lithium arsenide, I'm 100% sure. We spent a year doing a very careful job, understanding the photon energy dependence, everything. Latinger theorem works beautifully. Even though there is KZ dispersion and all sorts of complications, I can assure you it works.
But nobody would disagree with that, Gabby. For lithium,
well, no, if you have an orbital selective mode transition, you should not agree because you should
no. At a zero temperature, lithium ion arsenic is in the itinerant state.
Okay.
Yeah, let's have this discussion a bit later, right? Let's have the last talk. Yeah, let's thank Rong again. Yeah.
Thank you.
Thank you, Rong. Yeah, for a nice talk. Yeah, so Jianwei, it's your turn. Yeah, just go ahead. So we're running quite late. Yeah.
Okay. I'm going to share my screen.
Yeah, you can just carry on.
Okay. Great.